Hello everyone, in this video I will go over my solution to the problem named police stations. This problem is taken from a Codeforces Div 2 contest and is rated 2100. The learning targets associated with this problem is that by the end of this video you should be able to understand how the simple breadth first search can be modified to do multi-source breadth first search, which is basically breadth first search from multiple starting points simultaneously. Secondly, by the end of this video, you will be able to use edge coloring to mark edges as important or non-important in the breadth first search. So first, let's look at the abridged problem statement. You can read the whole problem statement over here, but what this problem is essentially asking you to do is, given a tree with n nodes and k special nodes which contain police stations, find the maximum number of edges to remove from the tree so that the distance from any of the other nodes to a police station node is less than or equal to d, and we need to print the indices of those edges which we have chosen to remove, with the only condition that we need to maximize the number of such edges which we choose to remove. So let's look at the sample test cases. In the first sample test case, we are given 6 nodes and we are given 2 police station nodes, which are nodes 1 and 6, and the distance which we need to have between a node and a police station node is at max 4, and you can verify that in this sample test case an optimal strategy would be to remove the edge from 3 to 4, which would make the distances from a police station node to a node which is not a police station 1, 2, 2 and 1, because the distance from the police station node 1 to 2 is 1, and similarly the distance from 1 to 3 is 2, and we have the exact same case with the other police station node 6, and you can verify that in the optimal case we would remove only one police station node. And since there are multiple answers, which is basically we removed the third edge in the input, but they chose to remove the fifth edge, and you can see that even if we remove the fifth edge, we would still get the same answer of 1, and all the nodes would still be less than or equal to 4 from a police station node. Now in the second sample test case, we are given 6 nodes again, and k is this time 3 with the distance being 2. So in this case, we have police station nodes 1, 5 and 6, and it should be obvious that the optimal strategy would be to remove the edges from 1 to 5 and from 5 to 6, because they are essentially useless, because 1 controls the tree and basically the distance from 1 to all the other nodes would be 1, and we can't remove any more edges because that would basically make the distance from a node to a police station node 1 infinite, because there'll be no path between them, and hence you can verify that the answer is 2, and you can also verify that there is only one set of nodes, and you can print either 4 5 or 5 4, which are basically the indices of the edges which you need to remove. So 1 to 5 and 5 to 6 are the fourth and fifth edges in the sample test case, and that's what we need to print. So now let's look at some of the ideas which we need to use to solve this problem. So the first idea should be that we need to minimize the distances from a node without a police station to a node with a police station. And since this is an undirected graph in which the edge weights are 1, that's why we can use BFS to find the distances between the k police stations to a node without a police station. And the way we are going to do that is by Multisource BFS, and the multiple sources or the starting points for a BFS will be basically the K police stations. And the second idea is that let's remove those edges which are not helping in the breadth first search. So first I define important to be that the edge is important if this edge will be used in the shortest path from some node to a police station node. And used in the shortest path essentially means that by using this edge you were able to reduce the distance from some node to a police station node. So these are the two key ideas, and now you can see that the not important nodes will basically be the answer. But there are two implementation details corresponding to these two ideas. First, we need to know how we will implement a multi-source breadth first search. So the multi-source breadth first search is actually a simple extension of the normal breadth first search, which is basically setting the K police station nodes to have a distance of 0. The distance of a police station node will be basically 0, and pushing those police station nodes to the queue. Then we run the normal BFS, and in the end what we get as a result of the BFS will be the shortest distance to every other node other than the police station nodes, because those nodes are at a distance of 0. So that's the first idea of multi-source breadth first search, and how we will implement the first idea basically. For implementing the second idea, which is basically finding the important edges, we'll use the edge coloring technique, which is going to be similar to the node coloring technique which I have covered in the previous few videos in the graph theory playlist. And the idea in the edge coloring technique is that you mark those edges which lead from a visited node to an unvisited node as important, and the remaining edges will basically be marked as unimportant. And this works because we need to use the important edges in the shortest path from a police station node to a non-police station node. And that's why if the edge leads from a visited node to an unvisited node, that means that we are reducing the distance of that unvisited node by using this edge, and hence that edge becomes important. In the end, the unimportant nodes are our answer. So now that we have got the idea on pen and paper, let's look at the code for this problem. So in the code, first I take in the values of n, k and d. Then I create an adjacency list of size n+1 because we are using 1 based indexing. An important thing to note is that we need to use a 3D vector because we need to store the indices of each edge, and this is generally a good idea when you're doing problems in which involve edges. So we create an adjacency list of 3 dimensions, and we'll basically take in those edges. So since the edges are again 1 based indexing, we run a loop from 1 to n-1, and we take in the 2 endpoints of the edges. And in this case, an important thing is that we are storing a pair of the adjacent node, comma, the index of the edge, and this is a small implementation detail which makes the code easier. And let's also take in the police station nodes. So we actually don't need to store those police station nodes, instead we need to push them to the queue. So we take in the first k nodes as the police station nodes. So these three would be the police station nodes, and we basically push that police station node to the queue. So I'm calling the police station node PS, and we push it to the queue after initializing or before initializing the distance to be 0. So for that we need a distance array which initially stores the distance of each node from a police station node to be infinite, which is 10 to the 9, and we initially mark the police station nodes to be at a distance of 0. And now we'll run the normal breadth first search, which will basically go to all adjacent nodes of the current node. So remember that since we are using a three-dimensional vector, the first value in the val vector will be the adjacent node, and the second value will be the index of that node. So that's why v and index correspond to those two entities. And if visited of v, so if not visited of v, then we'll basically mark the color of that edge to be important. Otherwise we'll basically not do anything, and we'll not mark anything. However, we need to have a visited vector which is boolean and initially false. We need to mark everything as visited when we reach that node, and once we reach that node we need to push it to the queue. And also we need to have a color array which stores the color of each edge. So remember that there are n-1 edges, but since we are using 1-based indexing, we need to do n-1 plus 1, which is basically n, and all the edges will initially be unvisited. And once we utilize an important edge, we'll mark it as important and visited. And let's basically define unvisited to be some number, let's say -1, and let's define important to be some number, let's say +1. And now let's just print the indices of the unimportant edges. So remember that the unimportant edges will be marked as not important, so which will not be marked as important. That means they'll be still unvisited in the end. So that's exactly what we need to do. For each I from 1 to n-1, if the color of that edge is unvisited, then we'll basically add that edge to our answer. For that we need a vector int answer, and we'll add that edge to the answer, and in the end we'll basically print the size of the answer and all the edges in the answer, which is basically the indices of those edges. You can see on the second sample test case we get the correct output of two edges, which are 4 and 5, and on the first sample test case we should get the output of 1, which is 3 as per the figure or the graph in the whiteboard. And now let's just submit the code to see that it gets accepted. So as you could see, my code got accepted. Returning back to the learning targets from the beginning of this lesson, you can realize that we have achieved the two learning targets of being able to understand multi-source breadth first search and being able to understand how to use edge coloring to mark the important edges in the breadth first search. So I hope you like this problem and my solution to this problem. If you like the video, don't forget to give it a thumbs up and do consider subscribing to my channel for more such content. Thank you.